For more than a decade, one spacecraft did exactly what it was built to do. No drama, no headlines, no mysteries. It moved through space with mechanical patience, circling Mars again and again, quietly measuring a planet that had already lost most of what once made it familiar. Its mission was not discovery in the cinematic sense. It did not search for life. It did not drill into ancient rock. It simply watched how a world slowly lost its atmosphere, particle by particle, year after year, sending back data that helped us understand how planets die. And then, without warning, it saw something it was never meant to see. The moment was brief, the opportunity was accidental, and the consequences were permanent. During a routine observation window, an unfamiliar object crossed its field of view. Not debris, not a known asteroid, not anything scheduled or expected. It appeared silently, moving through space on a trajectory that immediately made orbital models uncomfortable. For several hours, that spacecraft had the clearest, closest look any human-made instrument has ever had of an interstellar visitor now known as 3I Atlas. Those hours should have changed everything we know about objects that arrive from beyond our solar system. Instead, the spacecraft stopped working, not instantly, not dramatically, but completely. Less than 2 days after completing its observations, it went silent. Communications dropped, commands failed, telemetry vanished. The platform that had functioned reliably for years was suddenly gone, taking with it the only close-range visual record of 3I Atlas ever captured. The explanation came quickly, wrapped in familiar language. A technical anomaly, a software issue, a communication failure. Space is harsh. Hardware degrades. These things happen, and sometimes they do. But timing has weight, and patterns matter. Because the silence did not come randomly in the middle of a long mission. It came immediately after the single most unusual observation event the spacecraft had ever experienced. And the data it collected during that window did not return to Earth intact. It was labelled corrupted, unrecoverable, lost to cascading system errors. Coincidence has limits, and this is where the story stops being about a spacecraft failure and starts becoming about what we choose to look away from. In just days, 3I Atlas will pass closer to Earth than any confirmed interstellar object ever has. It is not a threat in the cinematic sense. There is no collision risk, no impact scenario, no apocalyptic trajectory. But proximity is not the same thing as danger. Sometimes proximity is valuable for a different reason. It forces clarity. And clarity is exactly what vanished when that spacecraft went dark. Because if 3I Atlas were unremarkable, if it were simply another cold fragment wandering through the galaxy, there would be no reason for its only close observer to become unusable at the exact moment it finished watching. There would be no reason for the data to disappear, no reason for silence to follow so neatly behind observation. Unless what was seen raised questions no one was prepared to answer publicly. And that leads to the uncomfortable possibility that the failure was not the beginning of the mystery, it was the response. To understand why that silence matters, you have to look at what 3I Atlas actually is, and why its behaviour immediately set it apart from anything we were prepared to classify. Interstellar objects are supposed to be rare, fast, and fleeting. They enter the solar system on hyperbolic trajectories, spend a short time within observational reach, and then disappear back into the dark between stars. Their velocities are extreme, their paths are clean, their interactions with the inner solar system are minimal. That's the theory. That's the expectation. That's what makes them scientifically valuable but operationally unthreatening. 3I Atlas followed none of those assumptions cleanly. From the moment it was detected, its trajectory forced astronomers to revise models more than once. Its approach angle was unusually shallow. Its relative velocity did not align neatly with typical interstellar distributions, and its brightness profile, how it reflected light across wavelengths, refused to settle into any familiar category. It did not behave like a classic comet, but it didn't behave like an inert asteroid either. its signature shifted subtly over time, as if its surface properties were changing in ways that could not be explained by simple outgassing or rotational effects. Individually, none of these traits would justify alarm. Space is full of oddities. Nature rarely respects our filing systems. But when multiple anomalies stack without collapsing into a clear explanation, scientists do what they always do. They watch more closely. And for a brief window, one spacecraft did exactly that. The platform that later went silent was uniquely positioned. It wasn't designed to study interstellar objects, but its instruments were sensitive enough to capture details that Earth-based telescopes could not. From its vantage point, 3i Atlas wasn't just a point of light against a black background, it was a resolved object moving against known stars, interacting with solar radiation in real time. Subtle variations became visible. Fine-scale behaviour emerged. Patterns that disappear when averaged over distance began to stand out. Those patterns did not make the object look dangerous. They made it look complicated. There is a crucial difference between those two words, and it's one that often gets lost outside scientific circles. Dangerous implies intent, force, immediacy. Complicated implies systems interacting in ways that are difficult to reduce, difficult to model, and difficult to predict. Complicated things don't have to attack you to cause problems. They only have to behave in ways your assumptions can't accommodate. 3i Atlas behaved like that. One of the first quiet red flags was thermal behaviour. As it approached the inner solar system, its temperature response did not match standard models. Certain regions appeared to warm and cool out of phase with rotation, suggesting either unusual surface composition or internal structure that was not uniform. That alone would be interesting. But combined with its spectral ambiguity, it raised a different question. Was this object reacting to solar input in a way that implied layered materials or something more dynamic? Again, this is not where the story becomes sensational. It becomes uncomfortable, because layered materials and dynamic responses imply a history. They imply processes. They imply that this object has been through environments that shaped it in complex ways, and those environments were not here, they were somewhere else, around another star under conditions we cannot directly reconstruct. The spacecraft saw that history up close, and then it stopped transmitting. Official statements described the failure as unrelated, a cascade of technical issues, aging hardware, a mission already beyond its nominal lifespan. All of that is plausible. All of it fits within the normal background noise of deep space operations. But plausibility is not the same thing as completeness, because the failure did not occur during years of routine operation. It occurred immediately after the most anomalous observation the spacecraft ever conducted. And more importantly, the failure pattern itself was not clean. It was not a single subsystem shutting down. It was a progressive lost communications first, then attitude data, then power telemetry, like a system that could no longer maintain internal coherence. That kind of failure is rare, not impossible, not unprecedented, but rare enough to invite questions, especially when the data collected during the final observation window did not simply fail to download. It degraded. Bits were lost. Packets arrived incomplete. Reconstruction attempts failed. What should have been a definitive dataset became fragmented enough to prevent independent analysis. And that matters, because science depends on redundancy. It depends on verification. It depends on multiple eyes looking at the same evidence and disagreeing productively until clarity emerges. When the only close observer goes silent and the data it captured becomes unusable, the process collapses inward. Interpretation becomes centralized. Uncertainty becomes managed rather than explored. This is the moment where stories usually split. One version says nothing unusual happened. The spacecraft failed. The objects passed. End of narrative. The other version asks a quieter question. What if the failure was not caused by 3i Atlas in the dramatic sense, but was triggered by interaction with an environment we did not fully understand? Not an impact, not a collision, but exposure. Interstellar objects are not just travellers, they are carriers of history. They move through regions of space that are chemically and physically different from the relatively sheltered environment of our solar system. They are exposed to radiation fields, particle densities, and dust populations that we model abstractly but have never sampled directly. When such an object enters the inner system, it does not arrive alone. It brings with it a local microenvironment shaped by its journey. For most observers, that environment is diluted by distance. For one spacecraft, it wasn't. The idea that proximity alone could matter feels counterintuitive. We're used to thinking in terms of impacts and forces, but in space, prolonged exposure to unfamiliar particle flux can be just as consequential. Fine dust at extreme velocities, electrically charged grains, exotic radiation interactions. These are not science fiction concepts. They are active areas of research precisely because their effects accumulate quietly, and accumulation is the enemy of assumptions. If 3I Atlas carried with it a denser than expected envelope of microparticles material trapped along its trajectory through interstellar space, then a close observer would have encountered something no mission had encountered before. Not a blast, not a strike, but a sustained interaction with a particle environment that was never part of its design envelope. That possibility alone does not explain the failure, but it reframes it. It shifts the story from something went wrong to something was different, and difference is where models break. What makes this more than speculation is the timing. The spacecraft functioned, it observed, it completed its window, and only then did the degradation begin. Not during the approach, not long before, after, as if the system absorbed something it could not immediately compensate for. There is a reason engineers worry about latent damage. Systems do not always fail at the moment stress is applied. They fail when accumulated stress crosses an internal threshold. That threshold is invisible until it is passed, and once passed, recovery is not guaranteed. Which brings us back to the silence. The loss of that spacecraft did not remove a single data point. It removed context. It removed the only direct comparison between pre-encounter and post-encounter system behavior. It removed the ability to ask the most important follow-up questions. And it did so at the exact moment those questions became unavoidable. Because 3I Atlas is still coming, and this time it will pass closer to Earth. What made the earlier interstellar visitors so manageable, at least in terms of public perception, was that they behaved like visitors in the simplest possible way. They came in fast, stayed distant, offered a short observational window, and left before anyone could attach a broader meaning to their presence. They were scientifically exciting, but narratively clean. They didn't intersect with our infrastructure. They didn't force operational decisions. They didn't seem to touch anything we depend on. 3I Atlas is different, not because it is bigger or louder, but because it is arriving at a time when we have built a thin shell of machines around our planet and convinced ourselves that this shell is stable. The modern world assumes orbit is reliable in the same way it assumes electricity is reliable. It does not think about the environment that keeps it reliable. It does not think about the fact that orbit is not empty, and that empty is a myth that only survives when the risks remain invisible. That is why proximity matters, even when there is no collision risk. A close pass is not just an opportunity for better images. It is an opportunity for interactions that do not show up as cinematic events. Dust flux, charging behavior, fine particle encounters that don't register as impacts, but as subtle stress on surfaces, sensors, and communications. In deep space, these effects are hard to isolate because everything is already extreme. Near Earth, they become easier to misinterpret because our expectations are calmer. We believe we know what normal space weather looks like here. We believe anomalies will announce themselves clearly. But interstellar objects don't have to announce themselves to change the local environment. They simply have to carry something unfamiliar into a region where our systems were designed around familiar baselines. The hard part is that unfamiliar doesn't mean exotic in the science fiction sense. It can mean statistically different. a particle population with a different charge distribution, dust grains with different surface chemistry, a slightly denser microparticle envelope that was trapped and shepherded along its trajectory. These differences sound small, and individually they might be small, but in space engineering, small differences can create large effects because systems operate close to tolerances and rely on assumptions remaining true over long periods. A spacecraft doesn't need to be struck by a visible object to be compromised. It can be compromised by the quiet accumulation of micro-erosion on critical surfaces, by changes in how it dissipates heat, by the way charge builds up on insulating layers, by the way signals propagate through a slightly altered plasma environment. Most of the time, these stresses are manageable because they are within expected envelopes. The danger is when something arrives that shifts the envelope without warning, leaving you with stress that looks like noise until it starts behaving like a pattern. This is why the only close observer matters so much, because it represents the one moment when we could have measured that envelope directly, compared it to baseline conditions, and learned something concrete instead of building theories out of distance and inference. The spacecraft wasn't just a camera, it was a witness to the question we almost never get to ask in space science. What does this object do to its surroundings when you get close enough for the details to matter? And then the witness went silent. That silence leaves two uncomfortable possibilities that are both difficult to live with. The first is that the failure really was ordinary, and the timing was coincidence. That would mean we lost the most valuable data set of the encounter for banal reasons, and the universe simply refused to cooperate. The second is that the encounter introduced a stressor that our systems weren't prepared to detect cleanly, and that stressor did not manifest as a dramatic impact, but as degradation that began quietly and became irreversible. If the second possibility is even partially true, then what matters about the next pass is not whether Atlas attacks anything. It is whether the conditions around it could interact with the most sensitive parts of our orbital infrastructure in ways that are easy to miss until they have already done their work. Because the current environment near Earth is not just a handful of scientific missions, it is a dense mesh of satellites, each one operating as part of a larger system. Navigation, communications, timing, weather monitoring, defense observation, shipping coordination, emergency response. The orbital shell is now a functional layer of civilization, and functional layers are fragile in a specific way. They don't need to break completely to cause harm. They only need to degrade unevenly. Uneven degradation creates uncertainty, and uncertainty spreads faster than failure. A single outage is a problem with a timestamp. Uncertainty is a problem that leaks into everything. It makes systems overcompensate. It makes operators increase complexity. It makes redundancies work harder. It makes the whole network more sensitive to stress at the exact moment it should be most resilient. This is why even a temporary environmental shift matters. If the passage of an interstellar object introduces, even briefly, a region where microparticle density is elevated, or where charging behavior becomes less predictable, it doesn't need to be catastrophic to matter. It simply needs to coincide with systems that are already operating with slim margins. And slim margins are becoming common as orbital traffic increases and constellations expand. The more crowded the orbit, the less room there is for uncertainty. The less room there is, the more every small disturbance matters. That's the real tension. The object itself may be harmless in the cinematic sense, but the context around it is not cinematic. It is infrastructural, and infrastructure fails in quiet ways long before it fails loudly. This is why the story refuses to be comfortable. It isn't about a giant rock on a collision course. It's about the difference between the space we think we live in and the space we actually operate in. We operate in a domain where dust can behave like bullets, where surfaces matter, where charging can degrade signals, where small particles can erase margin without leaving a headline behind. We operate in a domain where we don't get many close passes from interstellar visitors, And when we do, we treat them primarily as opportunities for pictures instead of opportunities to measure their local environments. And in this case, the one machine that might have turned opportunity into measurement is no longer responding. That is why the next pass matters. Not because it threatens impact, but because it threatens ignorance. It threatens to pass through our neighbourhood, influence our environment in subtle ways, and leave again without us being able to say with confidence what it did, how it did it, or what it implies about the next visitor after it. Because even if Atlas causes nothing visible, the question remains, why did the witness fail when it did? And what exactly did it encounter in the hours when it had the closest view we will ever have? A clean hardware death has a certain signature. It is abrupt. It is localized. A power subsystem fails and everything goes dark. A transmitter fails and you lose communications, but the spacecraft may still be alive internally. A computer resets and you see predictable reboot behavior. Even when failures cascade, they usually follow a path that engineers can reconstruct, because the cascade obeys the architecture. One component goes, then the systems that depend on it follow, and the pattern makes sense once you map dependencies. What made this failure so unsettling was that it didn't behave like a simple chain. At first, it looked like a communications issue, not unheard of. Deep space links are fragile and signal conditions can degrade for mundane reasons. But then came the second layer. Attitude data stopped arriving in a stable way. That is not just, we can't hear it. That is, it may not be holding itself. Then power telemetry became intermittent. Then the spacecraft stopped responding to commands that should have produced at least a minimal acknowledgement, even if its main mission systems were compromised. And this is the point where normal mission aging stops feeling like a complete explanation, because long-running spacecraft do not typically go from operational to non-responsive right after a unique observation event unless something changed in their environment, their internal state, or both. Aging creates gradual weakness. It erodes margin. It increases susceptibility. But it rarely chooses a dramatic, narratively perfect moment to finish the job, unless a threshold was crossed. Threshold failures are the hardest kind to diagnose, because they look like coincidence until you see enough of them. A system operates with intolerance until a specific stress pushes it just past what it can recover from. The stress might be small. The system might appear fine immediately after. Then, as internal compensation mechanisms run out of margin, the failure unfolds, not as a single event, but as a sequence of losses that look unrelated until you realize they're all downstream of one invisible change. This is why the order of degradation matters. When communications degrade first, it can suggest antenna pointing issues, transmitter performance drift, or plasma interference in the propagation path. When attitude stability then becomes questionable, it points towards sensors, star trackers, gyros, or reaction wheels operating under abnormal conditions. When power telemetry becomes unstable, it suggests load shedding, battery stress, or panel performance anomalies. None of these are proof, but together in a short time window they suggest a system that is fighting to remain coherent. And that kind of fight often begins with something that sounds almost too small to take seriously: surface effects. A close encounter with a particle-rich environment can do damage without drawing a clean line from cause to effect. Fine particles can pit coatings and optics, degrading sensor performance just enough to increase attitude control workload. Charging effects can produce electrostatic discharge events that upset electronics without permanently frying them, leaving behind intermittent faults that worsen over hours. Microerosion can change thermal behavior, shifting temperatures into regimes where oscillators drift and systems become noisier. Noise forces control systems to work harder. Harder work consumes power. Power stress exposes every weak link. None of this is dramatic. It is the kind of physics that ruins missions quietly. And there is another detail that makes the failure behavior difficult to dismiss as just old age. The data itself did not merely fail to transmit. It degraded in a way consistent with instability. When a spacecraft is healthy but out of contact, Data typically remains intact on board until it can be downlinked later. When a spacecraft is unstable, when power cycles, resets, or memory corruption occurs, data can become fragmented. Packets can be lost, files can be partially written, compression streams can break. A dataset that should have been the most valuable becomes precisely the one most likely to be corrupted if the system is fighting for continuity. That is exactly what appears to have happened. Not a neat loss, a messy one. And messy failures are where the uncomfortable questions live, because messy failures imply the spacecraft was not simply dead. It was struggling. It was degraded in a way that interfered with its ability to preserve and deliver its own record of what it saw. Which leads to a quiet but essential point. If this were purely a communications problem, the spacecraft could have been recovered later. If it were purely a pointing problem, operators might have stabilized it. If it were purely power-related, they might have reconfigured loads. But when multiple subsystems degrade in a tight sequence after a close encounter, recovery becomes unlikely, not because no one tries, but because you're dealing with compounded uncertainty. You don't know what is failing, so every command becomes risk. Every attempt to force a response may push a weakened system further into instability. In other words, once the threshold is crossed, the window for calm troubleshooting closes quickly. This is also why public narratives around these failures are often conservative. Agencies and teams choose explanations that protect confidence and avoid speculation, because speculation does not restore a spacecraft. But conservative language can hide the most important scientific clue. The timing and texture of failure sometimes matter more than the official label. A technical anomaly is a category, not a cause. And if Atlas had anything to do with this, it would not be because it fired a beam or caused a mechanical crash. It would be because the spacecraft entered a local environment that was different enough to spend margin rapidly, crossing thresholds that years of routine operation had not crossed. That idea becomes more plausible when you remember what we do not have. We do not have a baseline measurement of Atlas's local particle environment at close range. We do not have direct sampling. We do not have corroborating close observers. We have one witness, one window, and then silence. Which means that the most valuable information may not be in the object's appearance alone, but in the way the observing platform failed afterward. Because failures leave fingerprints. Not always obvious ones, but patterns. If you want to get closer to what those patterns might imply, there is a second layer that matters even more than subsystem order. The way the spacecraft stopped responding suggests not a single fatal strike, but a loss of confidence inside the system. A platform can survive many small errors as long as it trusts its own sensors and can maintain stable control. When it can't, everything else becomes fragile. And that brings the story to a point that feels almost unfair. The very systems designed to keep a spacecraft safe, automatic fault protection, safe modes, autonomous resets, can become traps when the environment creates ambiguous intermittent faults. The spacecraft tries to protect itself. It enters safe mode, it shuts down instruments, it points to the sun, it resets, it tries again. Each cycle consumes power, time, and data integrity. Each cycle can worsen corruption if the underlying stressor persists. A protective reflex becomes a loop, and loops are how quiet damage becomes permanent. So the question isn't whether a spacecraft can fail after a rare observation event. It can. The question is whether the failure pattern looks like the kind of loop you'd expect from an environment-induced stress that doesn't deliver a single clean blow, but instead destabilizes the platform until it can no longer preserve itself. Because if that's what happened once, then the next pass matters, in a way that is hard to dramatize but easy to understand. It means the danger isn't impact, it's exposure. And exposure is the kind of risk that can touch many systems at once, while leaving almost nothing visible behind, until you start counting anomalies, and you realize the anomalies are no longer random. Near Earth, we've built a kind of invisible city, not one you can see from the ground, but one that exists as a shell of machines, thousands of satellites, each one small in isolation, collectively forming a layer civilization leans on every day. The reason this matters is simple. When the environment shifts slightly, the effects don't have to be dramatic to become real. They only have to be widespread. A particle-rich local environment, especially one with unusual charging behavior or a different dust grain distribution, doesn't need to hit satellites like a projectile to matter. It can change how surfaces behave, it can change how sensors see, it can change how signals propagate. And because modern satellites are designed to be efficient, they run closer to margins than people realize. They're built to survive expected conditions, not unknown ones. The first failures, if they happen, won't look like a crisis. They'll look like maintenance, a few extra safe mode entries, a little more pointing jitter, a small rise in star tracker dropouts, a handful of thermal anomalies that resolve themselves, power performance that's slightly worse than predicted but still acceptable. This is how a system gets used to stress. It absorbs it operationally. It doesn't announce it publicly. But a dense orbital environment has a feature that makes small stress dangerous. Correlation. When many satellites share similar orbital corridors, they share exposure. When exposure becomes correlated, the anomalies stop being isolated. They begin to cluster. Even if each anomaly is minor, clusters change fleet-level reliability. And fleet-level reliability is what the world actually depends on. Because GPS and timing services don't rely on one satellite. They rely on constellations behaving consistently enough to provide stable outputs. Communications networks don't rely on one platform. They rely on layers of redundancy behaving predictably. Weather monitoring, Earth observation, shipping coordination, emergency response. These systems assume continuity and graceful degradation. They assume that if something fails, it fails rarely, independently, and with enough warning to compensate. A correlated stressor attacks that assumption without ever looking like an attack. What makes this relevant to Atlas is not the fantasy that an interstellar object brings doom. It's the far more grounded possibility that an interstellar object carries a local environment we don't fully characterize, and that environment could briefly intersect with a region where we've placed an enormous amount of fragile infrastructure. The danger, if there is one, would be statistical. It would be the temporary tightening of a probability field around systems that already operate near tolerance. That kind of danger is almost perfectly designed to be dismissed at first, because in space operations you expect noise, you expect anomalies, you expect occasional losses. When one satellite misbehaves, you don't reach for extraordinary explanations. You reach for the probable ones: aging, software, manufacturing variants, space weather. That conservatism is healthy, but it also creates a blind spot. If a new stressor arrives and expresses itself as a small increase in anomaly rates, it can hide inside what you already call normal, until the increase becomes large enough to notice. And by then the question shifts from what caused this to how do we keep services stable while we investigate. That's the moment the system begins consuming margin as an operational strategy. And margin, once consumed, reduces resilience. Reduced resilience makes future anomalies more costly. More costly anomalies create pressure to replace and accelerate. Acceleration increases congestion. Congestion amplifies every risk, including the quiet ones. This is how you can turn a temporary environmental phase into a long-term problem without any single dramatic event. And that's why the earlier spacecraft failure matters as a warning sign, even if it can't be proven as causal. It shows what exposure can look like when it crosses a threshold. A platform that was stable becomes unstable. Data becomes corrupted. Recovery becomes uncertain. The mission ends, and the most valuable record disappears at the moment it becomes most important. Now scale that vulnerability from one spacecraft to 1,000 satellites that share similar orbits. You don't need Atlas to destroy anything for the next pass to matter. You only need a brief environmental change dust density, charging conditions, microparticle flux large enough to push a fraction of satellites into higher fault rates during the same window. The world would not see a single catastrophic outage. It would see unevenness, glitches, corrections, workarounds, Small disruptions that look unrelated until someone compares logs across operators and realizes the anomalies are clustering in time and geometry. And then, once again, the problem would not be the object itself. The problem would be what we can't confidently measure, because in the absence of direct local sampling, you are left with inference. You are left with post-event pattern analysis. You are left with the question we already faced once. Did something external shift the environment, or did we simply notice our own fragility at an inconvenient time? That question is not academic. It determines what you do next. If you believe it's random aging, you replace and move on. If you believe it's an environmental phase, you monitor, coordinate, and adjust operations to preserve margin. Those two responses lead to very different futures in a crowded orbit. This is where the story tightens into its real hook. Because if Atlas is carrying a local particle environment different enough to matter at close range, then the most valuable thing we could do is measure it directly while it's here. Not after, not in hindsight, during. But the only spacecraft that saw it up close is no longer talking. And that leaves us with a dangerous gap. A moment of maximum scientific opportunity paired with minimum measurement capability. So the question becomes uncomfortably practical. If we can't measure Atlas directly, how do we detect its effects? And how do we do it fast enough that the first signs don't get normalized as routine noise, until the archive, years later, reveals the pattern we should have seen in real time? If you can't measure the object directly, you measure the footprint it leaves in the systems that live near it. Not because those systems will announce, "This was Atlas," but because complex infrastructure has a habit of responding to unfamiliar stress in consistent machine-like ways. It produces signatures, and signatures are often easier to detect than causes if you know where to look and if you stop pretending every anomaly is isolated. The first place you look is not the public-facing performance. Public-facing performance is designed to be smooth. It's the last thing to change because it's what operators protect at all costs. You look instead at the layers that exist beneath the surface: telemetry, fault logs, safe mode entries, attitude control correction rates, star tracker dropout frequency, unscheduled resets, unexpected thermal excursions, power regulation irregularities, transmitter error rates, anything that indicates the system is working harder than usual to remain stable. You're not hunting for a single dramatic spike, you're hunting for clustering. Because if the stressor is environmental, it won't strike one satellite like a lightning bolt and spare the rest. It will raise the probability of small failures across many satellites that share exposure geometry during the same window. The pattern won't be everything breaks. The pattern will be too many small things happen at once in a way that violates independence. That independence assumption is the quiet foundation of modern reliability. We assume faults are mostly random. We assume manufacturing defects are distributed. We assume radiation upsets occur, but not in synchronized pulses unless a known solar event explains them. We assume that if a few satellites misbehave, the rest carry the load. That's why constellations work. A corridor-like environmental change breaks that assumption without making a sound. So the most useful question becomes, what would correlated stress look like in the data? And the answer is uncomfortable, because it looks like the kinds of problems engineers are trained to treat as mundane. It looks like extra corrections. It looks like small degradations that still remain within spec. It looks like work. But the difference between mundane work and environmental stress is that mundane work doesn't line up across fleets unless something bigger is shaping it. You'd start with time. Do multiple operators see increased fault activity during the same hours? Then you'd add geometry. Are the affected satellites concentrated in similar orbital altitudes, inclinations, or local times? Then you'd look at environmental context. Was there a known solar event, a geomagnetic storm, a predicted meteor stream? If none of those explain the clustering, the anomalies stop being random noise and start being a signal that the baseline may have shifted temporarily. And then you'd do the step that is hardest politically and easiest scientifically. You would share enough data to compare, not the secrets, not the proprietary details, just the fingerprints, because fingerprints don't belong to one operator. If the environment changed for everyone in that corridor. This is where the story becomes almost painfully modern. We have the computing power to correlate huge datasets. We have the tracking networks to monitor large debris. We have the satellites. We have the logs. What we often don't have is the habit of treating subtle anomaly statistics as a shared environmental instrument. We treat them as local problems because local problems are easier to own. Shared problems require shared responsibility, and shared responsibility is the one thing competitive systems resist, until the cost of resisting becomes higher than the cost of cooperating. That's how it always goes. So the most unsettling version of the next pass is not that satellites suddenly start falling out of the sky. The unsettling version is that the next pass happens and a weak signal appears, an uptick in clustered anomalies that lasts a day or two, and the world simply calls it routine. Operators patch around it. Teams file tickets. A few platforms are replaced early. Nothing that becomes a headline. Then Atlas leaves, and the system returns to baseline. And by the time anyone is willing to connect the dots, the window for direct measurement is closed. That would be the perfect quiet failure. Not the failure of hardware, but the failure of attention. Because the first sign will never feel like proof. It will feel like inconvenience. And that is exactly why the story of the lost close observer matters. The difference between learning and guessing often comes down to whether you can treat inconvenience as data, whether you can resist the urge to explain it away as normal, at least long enough to ask if it's part of a larger shape. If you're building a watch list for the next pass, you'd focus on 3 categories of signatures that can rise during unusual particle or charging environments without requiring an impact event. First, attitude control and sensor stability signatures, star tracker dropouts, increased gyro bias drift, higher reaction wheel activity, pointing jitter, and more frequent safe mode entries triggered by loss of confidence in orientation. Second, power and thermal signatures, unexpected temperature swings, altered radiator behavior, temporary power regulation irregularities, battery depth of discharge anomalies, and slight reductions in solar panel efficiency that don't match expected eclipse patterns. Third, communications and signal propagation signatures, higher bit error rates, intermittent link margin reductions, and anomalies that correlate with local plasma conditions rather than with hardware changes. None of these are definitive, but together they can tell you something simple and actionable. The environment is behaving differently than expected, and that is all you need for the first step, because the first step isn't proving an interstellar object did something. The first step is recognizing that the risk field may have shifted, and that the safest response to a shifted risk field is disciplined monitoring and conservative operations, not accelerated congestion. If this sounds almost too cautious, remember what the alternative is. The alternative is waiting for a visible failure to justify attention. Visible failures are expensive in orbit, and the most expensive part is that they narrow your options. They force fast decisions. Fast decisions tend to increase traffic. Increased traffic tightens every margin, and when margins are tight, the next weak signal becomes the next quiet cost, and the loop continues. That's why the next pass isn't just a scientific curiosity, it's a rare chance to practice maturity in real time. Because if the corridor-like idea is even partially true, if proximity to Atlas correlates with a temporary rise in microparticle flux, or unusual charging behavior, or a local statistical tightening of environmental conditions, then the best evidence may never be a photo. The best evidence may be the pattern of how our machines behave while the object is nearby. That's the inversion people don't expect. We're used to thinking that we learn from what we see. But in complex systems, we often learn more from how our instruments struggle than from what they capture when everything is easy. And it's also the reason this story remains calm, because calm is what you need to detect weak signals. Panic makes you hunt for drama. Drama makes you miss patterns. Patterns are where the truth lives when the truth is subtle. So the real question heading into the next pass is not what will Atlas do. The real question is, Will we be disciplined enough to notice what our own systems are telling us while we still have time to learn from it? Because if we aren't, the archive will grow again. Another year of scattered logs, another set of anomalies treated as local problems, another missed chance. And then, 20 years from now, someone will unify the record and discover that the wave was visible all along. If only we'd been willing to listen when it sounded like nothing. The next pass isn't a long season. It's a narrow corridor in time, and once it closes, it doesn't reopen on human schedules. That's the cruel part. We can build bigger telescopes, we can improve our models, we can argue about probabilities for years. None of that changes the fact that proximity is a one-time condition, and proximity is what turns speculation into measurement. During the closest window, every serious observer will try to do the same thing. Turn Atlas from a moving dot into a measurable system. They'll chase sharper imagery, deeper spectroscopy, polarimetric signatures, thermal curves, rotation states, and any hint of outgassing or dust shedding. They'll try to constrain mass, density, albedo, and surface composition. They'll look for a coma that isn't obvious. They'll watch for faint tails and transient jets. They'll compare dayside and nightside behavior and search for thermal inertia patterns that tell you how heat moves through the object. They'll ask the simplest scientific questions that hide the hardest answers. What is it made of, and how has it survived the journey? But the most important attempt may not be about Atlas itself. It may be about the space around it. Because the moment you accept that exposure could matter, the most valuable measurement becomes environmental. Does the region near Atlas show an elevated microparticle flux? Does it distort local plasma conditions? Does it change charging behavior on nearby spacecraft? Does it correlate with sensor instability or link margin anomalies? Those questions don't require a dramatic effect. They require clean instrumentation and disciplined logging, and that's exactly what modern systems are not optimized to celebrate. Most missions are built to observe targets, not to act as environmental buoys. Most operators are paid to deliver service, not to publish anomaly fingerprints. And most scientific campaigns focus on what can be seen, not what must be inferred from how instruments behave. That's why the window is so high stakes in a quiet way. It offers a chance to do the one thing we almost never do well: measure subtle interactions while they are happening, before the story turns into reconstruction. Because reconstruction is where narratives drift. It's where uncertainty becomes political. It's where people choose the explanation that creates the least friction, rather than the explanation that best fits a messy pattern. It's also where missing data becomes a permanent wound, because the things you can't measure later are exactly the things you needed to measure early. If you want to avoid repeating the failure of the Lost Close Observer, the approach has to be different this time. Not louder, different. Instead of chasing one perfect photo, the disciplined approach would build redundancy in the right places. Multiple independent instruments watching the same basic parameters. Multiple platforms comparing telemetry in real time. Anomaly thresholds that trigger higher resolution logging rather than quiet resets. Correlation pipelines that treat small fault clusters as environmental signals until proven otherwise. The goal wouldn't be to accuse Atlas of anything. The goal would be to avoid the single biggest mistake we've already made once, letting the most valuable clues vanish inside the category of routine. Because the most dangerous phrase in this story is not interstellar, it's nothing unusual. Nothing unusual is what you say when you don't have the instruments to see unusual. Nothing unusual is what you say when your systems are compensating successfully. Nothing unusual is what you say when the anomalies are small enough to be annoying, but not large enough to be undeniable. Nothing unusual is what you say when you're already too busy to connect the dots. If Atlas passes and nothing dramatic happens, the public story will end right there. It will be described as a scientific curiosity, a rare visitor, a few new images, a few new papers, and then a fade out into the next distraction. But if you're paying attention to the deeper question, the story doesn't end with the public. It continues in the logs. It continues in the telemetry. It continues in whether fault rates line up in time, whether link margins dip in clusters, whether attitude control activity rises in corridors, where the satellites that share geometry show small, synchronized stress. In other words, the real evidence may not be something you can show on a thumbnail. It may be something you can only see if you decide ahead of time that you are going to look for it. And this is where the "we did this to ourselves" idea becomes more than a moral. It becomes a practical vulnerability. Because even if Atlas carries a slightly unusual microenvironment, that microenvironment only matters to the extent that our orbital shell is already dense, already sensitive, already operating with slim room for correlated stress. If orbit were sparse, anomalies would remain isolated. If traffic were low, operators would have more time and margin to respond. If disposal compliance were perfect, the background would be cleaner. If redundancy were generous, small stresses would wash out. But we don't live in that version of orbit anymore. We live in a version where small changes can become expensive simply because the baseline is crowded and the dependencies are deep. That means the true risk is not Atlas itself. The true risk is that Atlas becomes an event that reveals how fragile our assumptions have become, and we respond the way busy systems always respond, by normalizing the signal until it becomes impossible to ignore. That is why the next pass feels like a test. Not a test of whether the sky is dangerous, but a test of whether we have matured past the habit of learning only from pain. Because this window offers a chance to learn calmly. It offers a chance to coordinate without a disaster forcing the coordination. It offers a chance to treat weak signals as valuable, while the stakes are still manageable. And the reason this matters is simple. The next interstellar visitor will come to, not tomorrow, not on schedule, but inevitably. If Atlas is truly unremarkable, this pass will still teach us something about interstellar materials and trajectories. If Atlas is anomalous in subtle environmental ways, this pass becomes even more important, because it may be the first time we can test a hypothesis that has been sitting uncomfortably in the background since the lost close observer went silent. That proximity can matter without impact, and that different can be enough to cross thresholds in systems that were never designed for that kind of encounter. Either way, the outcome depends less on the object and more on us, on whether we build a watch list ahead of time and commit to reading it seriously, on whether operators are willing to compare anomaly fingerprints instead of treating them as private inconveniences, on whether we can resist the comfort of nothing unusual long enough to be sure we've actually looked, on whether we can accept that the most valuable measurement may be the behavior of our own machines, not just the light reflected off a visitor. Because if we can't, then the story repeats in the most predictable way. Atlas passes. A few satellites show mild, explainable problems. No one connects the dots. The window closes. And later, when scattered records finally align, we realize we could have known earlier, if only we had treated the weak signals as worth the effort while they were still cheap. That is the quiet risk of this moment. Not a disaster. A missed chance. And in crowded systems, missed chances accumulate the way dust does. They don't look dangerous at first. They simply make the next event harder to understand, harder to manage, and more expensive to respond to. Which is why the final tension is not in the sky. It's in whether we can do something humans rarely do without being forced. Pay attention while it still feels optional. If you want a version of the events that stays grounded, avoids melodrama, and still explains why the timing feels wrong, it starts with a simple engineering truth. Spacecraft rarely fail at the exact moment they encounter stress. They fail when the stress has already been absorbed and the system is trying to recover. That delay is what makes threshold failures so deceptive. The platform looks normal right after exposure because the damage is not always a broken part. It can be a change in behavior, a new level of noise, a weak signal that becomes just weak enough to trigger the next protective response. Then the protection stack, the margin shrinks, and the failure unfolds like a slow collapse of confidence. That loss of confidence phrase matters more than it sounds. A spacecraft is not a single machine. It's an argument between sensors, software, and physics. The software believes the sensors. The control system believes the math. The power system believes it can keep everything running long enough to recover. Safe modes exist to preserve that belief. When something introduces intermittent ambiguity errors that come and go, faults that don't repeat cleanly, those protective systems can become a trap. The spacecraft keeps trying to protect itself from what it can't name. It resets, it reconfigures, it enters safe mode, it reduces load, it attempts to re-establish attitude and comms, and each cycle costs power and time. If the underlying stressor continues for long enough, or if the stress has already pushed a subsystem past its stable operating region, those cycles don't rescue the mission. They just consume the last reserves that would have made rescue possible. Now apply that to a close observation window near an interstellar object. Not an impact, not a collision, a different local environment dust grains at unusual velocities, a charge distribution that changes how insulating surfaces behave, a plasma condition that makes certain sensors noisier than expected. You don't need a weapon to produce weird outcomes. You only need the spacecraft to encounter conditions it was never designed to interpret correctly. A star tracker doesn't have to break to become unreliable. It only has to receive a slightly altered background signature, a slightly different scattering pattern, or suffer micropitting on optics that increases stray light. A communication system doesn't have to lose its transmitter to struggle. It only needs its link margin reduced intermittently by propagation conditions it wasn't tuned for. A power system doesn't need a dramatic failure. It can be drained by repeated protective loops, each one rational, each one expensive. This is where after becomes more suspicious than during. During the observation, the spacecraft can still perform because the system is spending margin to hold itself together. After the observation, when it tries to stabilize, dump data, reset into its routine, and rebalance thermal and power states, the accumulated stress begins to show. The platform may enter protection logic more often. It may oscillate between modes. It may lose attitude lock briefly and regain it repeatedly, until it fails to regain it one last time. It may corrupt data not because the data was never recorded, but because the recording and storage process was interrupted by resets, partial writes, or power cycling. It may become a machine that is still technically alive, but no longer coherent enough to talk. That kind of failure is almost impossible to prove after the fact if you don't have clean logs from the exact window of degradation. And that is the cruel symmetry in this story. The same kind of stress that would cause a threshold failure is also the kind that can damage the evidence you'd use to confirm it. The witness doesn't just stop speaking. It loses the ability to preserve its testimony. This is why the story leans on patterns instead of claims. It doesn't need to say Atlas destroyed the spacecraft like a headline. It only needs to say something harder to dismiss and easier to respect. The failure sequence is consistent with exposure-induced destabilization. The timing is aligned too neatly to ignore, and the loss of the dataset removes the one thing that would allow independent teams to settle the debate. What remains is a gap filled by comfort phrases, aging hardware, technical anomaly, harsh environment phrases that may be true and still incomplete. And if that sounds like a weak conclusion, it isn't. In complex systems, incomplete is often where the real risk hides, because incomplete explanations preserve habits. They allow the system to keep doing what it was doing. They keep operators from building new watch lists, new logging rules, new correlation pipelines. They keep the next weak signal labeled as routine, and routine labels are what create archives that only make sense years later, when the cost is already paid. So the cleanest way to connect this back to your title, the fact that we miss something for years, is to admit what missing looks like in practice. It doesn't look like incompetence. It looks like normalization. It looks like the human habit of turning strange events into ordinary ones as quickly as possible. Because ordinary events don't demand expensive change. It looks like choosing the safest public explanation, because safe explanations protect trust. It looks like treating mission loss as a sad but acceptable cost of exploration, rather than as a potential environmental clue. It looks like the refusal to build a shared map of weak signals, because weak signals are inconvenient and easy to argue about. And then, one day, the facts line up. A mission dies right after a close look. The data is corrupted. The trajectory is unusual. The signatures are ambiguous. The timing is too perfect. And the next pass is close enough that we should care about measuring the environment, not just the object. That alignment forces a question that is both fair and uncomfortable. If the failure was even partly related to exposure, what does it imply about the systems that now occupy near-Earth space in far greater numbers than ever before? Not that they will be taken out, but that they may be more vulnerable to unfamiliar phases than our culture of averages is willing to admit, because the real vulnerability is not that something strange might happen once. The real vulnerability is that if something strange happens in a way that looks like routine noise, we will treat it as routine noise until the window closes. We will replace what fails, we will patch what drifts, we will file tickets, we will continue delivering service, and we will tell ourselves the world is stable because the output remains stable. Then later we will unify records and discover that the stability was purchased with invisible effort and shrinking margin, and that the shift had a signature all along. That is the "we did this to ourselves" part, and it isn't about blame. It's about design choices that prioritize deployment speed over shared measurement, competitive secrecy over comparability, and comfort narratives over environmental curiosity. We built a crowded orbit and then acted surprised when the environment became harder to interpret. We built systems that hide their strain so the public can enjoy smooth outputs, and then forgot that hidden strain is itself a warning metric. We taught ourselves to look for drama, and then ignored the quiet signals that actually govern long-term resilience. So if you want the next pass of Atlas to mean something, the goal isn't to prove a sensational claim. The goal is to prevent another loss from becoming another missing dataset. The goal is to treat any clustered anomalies, however small, as a temporary environmental episode worth analysing collectively, while the analysis can still change behaviour. The goal is to build the habit that turns one weird coincidence into a measurable pattern in real time. Because if the only close observer failed once after looking at Atlas, the most responsible assumption is not that history will repeat perfectly, but that the same kind of blind spot can repeat. The blind spot where weak signals get normalized, and the price of normalization is paid later in the form of reduced margin and fewer options. And this is where the story can make its promise honestly. Not that Atlas will do something dramatic, but that this time, if anything subtle happens, we can choose not to miss it. We can watch the right data. We can compare the right fingerprints. We can treat the annoying anomalies as the story instead of waiting for a disaster to make the story obvious. And if we do that, then even a quiet pass becomes valuable, because we either confirm that the environment remains within baseline expectations, or we detect that something about proximity changes the probability field in ways that matter. Either outcome teaches us something real about how interstellar visitors interact with modern orbital infrastructure. But if we don't do it, if we treat the next pass as a photo opportunity and nothing more, then the story ends the way it always ends when systems normalize weak signals. The window closes, the logs scatter, the archive grows, and the lesson arrives later when it costs more. The temptation in moments like this is to make the right response sound heroic, because heroism sells. But the truth is simpler and more demanding. The only meaningful response is procedural, and it has to happen before anyone knows whether it will be needed. That's what separates a calm, mature infrastructure from a reactive one. A mature system prepares to detect weak signals because it understands weak signals are how the real story begins. A reactive system waits for visible failures and then calls the visible failures the beginning, even though they're usually the late stage of something quieter. So the question isn't whether Atlas deserves a panic. It doesn't. The question is whether Atlas deserves a disciplined window of monitoring that treats nothing unusual as a hypothesis you test, not a phrase you default to. Because a phrase is cheap and a test is work, and work is what busy systems avoid until the cost of avoidance becomes unbearable. If you were building that test, you wouldn't start by trying to catch Atlas doing something. You'd start by defining what you would accept as a meaningful deviation from baseline, not a headline, a deviation, a measurable, time-bounded shift in anomaly, clustering that cannot be explained by known space weather, known debris events, or expected seasonal patterns. You'd define a corridor in time around closest approach and widen it enough to detect lead and lag effects, because threshold failures don't obey a clean timestamp. You define which orbital bands and geometries are most likely to share exposure, and then you decide in advance what you will do if the weak signal appears. Not public statements, not speculation, but heightened logging, comparative analysis, and conservative operations that preserve margin while the episode is being understood. That last part is where systems usually fail, because preserving margin feels like sacrifice. It feels like doing less when the instinct is to do more. But margin is the only thing that gives you options, and options are the only thing that keeps an episode from becoming a loop. When a corridor tightens, the wrong response is to accelerate congestion and burn reserves to maintain the illusion of normal. The right response is to slow, measure, and let the environment tell you what it is doing before you force your infrastructure into the most brittle state it can occupy, constant compensation. The irony is that we already have the instruments, in a way. Not perfect instruments, not dedicated environmental probes in every corridor, but a global fleet of machines that continuously reports what it is struggling with. Every safe mode entry is a sentence, every pointing dropout is a syllable, every unexpected thermal excursion is a word, a single event can be dismissed. A clustered pattern across operators becomes a language if you're willing to translate it. The translation requires two things humans resist: comparability and patience. Comparability means aligning how logs are recorded, how anomalies are classified, and how minor issues are tagged so they can be aggregated. Patience means refusing to close the file too quickly. It means letting an episode remain open long enough to see whether the shape repeats in geometry and time, rather than forcing it into the comforting category of random. And this is where the lost close observer becomes more than a dramatic anecdote. It becomes a warning about how quickly a rare window can be squandered. The spacecraft didn't just fail, it failed in a way that took the record with it. It turned what should have been the most clarifying data set into an absence. It created a silence that allows comfortable stories to survive. If the only close observer goes dark, the easiest narrative is the one that preserves normality. Hardware ages, missions end, space is harsh, move on. The harder narrative is the one that asks what the failure might be telling us about exposure and thresholds, and whether we have the humility to treat that question as legitimate even without perfect proof. Because proof, in a case like this, is not a single image. Proof is a pattern that survives multiple interpretations. Proof is a correlation that holds across operators who do not benefit from inventing it. Proof is a deviation that appears where it shouldn't, repeats where it should not repeat, and fades when the window closes. That's the kind of proof a quiet story can actually produce if you decide in advance to gather it. If you want the clearest hook to keep in mind, it isn't a dramatic claim. It's a simple dilemma. An interstellar object is passing close enough to our orbital shell that any subtle environmental effects, if they exist, would be easiest to detect right now. The only spacecraft that saw it up close is no longer available, and the world has become dependent on orbital systems that can be stressed by subtle, correlated shifts without anyone noticing until later. That combination isn't a reason to panic. It is a reason to act like adults. Adults don't panic, they monitor. Adults don't assume, they verify. Adults don't wait for the expensive lesson, they pay for the cheap measurement. And if we do that, the outcome is valuable no matter what we find. If the window passes cleanly, no clustering, no unexplained upticks, no geometry-linked anomalies, then we've gained something we rarely gain. Confidence grounded in observation rather than comfort. we will have tested a hypothesis and closed it honestly. That matters because it tells us our current baselines are more robust than the uneasy narrative suggests. It also teaches us how to coordinate and compare in real time, which is useful for every other environmental episode orbit will face, interstellar or not. But if the window does not pass cleanly, if we see small clusters in the right corridors, if the signatures rise and fall with the passage window, if independent fleets see similar fingerprints, then we have learned something far more important than Atlas is weird. We have learned that subtle environmental phases can express themselves through our infrastructure in ways that are detectable only when we choose to treat weak signals as data rather than as annoyance. Either way, the lesson isn't about Atlas alone, it's about the kind of civilization we are building in orbit. Because civilization doesn't fail when a single machine dies. Civilization fails when it loses the habit of preserving resilience and learning early. Civilization fails when it normalizes the slow costs until the slow costs become the new baseline. Civilization fails when it trades measurement for narrative because narrative is easier to live with in the short term, even though it is more expensive in the long term. And that's why this story circles back to responsibility without turning into blame. We did this to ourselves. Doesn't mean someone is guilty of a single decision. It means we collectively scaled an environment faster than we scaled the maturity required to monitor it. We deployed faster than we standardized. We competed harder than we cooperated. We treated orbit as a platform rather than a living variable domain. And we made those choices because the system kept working, which is the most seductive excuse in engineering. It works, therefore it is safe. That logic is only valid until the day a weak signal becomes a pattern, and the pattern becomes a constraint, and the constraint arrives during a week when the world is already stressed. So if you want the simplest promise this story can make, it's not that Atlas will change everything. It's that this is a rare chance to change how we behave, while nothing is visibly wrong. It's a chance to decide that a clean pass means clean because we measured it, not because we assumed it. It's a chance to decide that if subtle anomalies appear, we won't let them vanish into private logs and comfortable explanations. We'll compare them. We'll correlate them. We'll treat them as a shared environmental signal until proven otherwise. We'll preserve margin instead of spending it to keep everything looking effortless. Because effortless output is not the same thing as stable infrastructure. Effortless output can be a mask. It can be produced by people working harder in the background while machines consume their last buffers. And when buffers are gone, the next episode doesn't have to be big to be costly. It only has to arrive at the wrong time. That's the real reason the Lost Close Observer still matters. It's a reminder that rare windows do not wait for us to be ready. And it's a reminder that when we lose a witness, we don't just lose data, we lose the ability to settle arguments cleanly. We lose the chance to learn cheaply. We lose time. And time is what orbit punishes us for wasting, because orbit is a domain where every small mistake leaves a footprint that persists. So as Atlas approaches and the window tightens, the question isn't whether the story is frightening. The question is whether we finally treat the calm years like the years that matter. Whether we build the boring scaffolding that keeps quiet signals from becoming quiet failures. Whether we accept that the most valuable thing we can do is listen, even when listening feels like work, even when the result might be nothing unusual, even when no one will applaud a prevention that leaves no dramatic event behind. Because that is what real maturity looks like in shared environments, and orbit has become a shared environment whether we admit it or not. In most stories, losing the only close observer would be the turning point, the moment the narrative becomes loud. People would demand explanations. Questions would multiply. The event would be treated as extraordinary because it feels extraordinary. But space doesn't behave like a story. Space behaves like a system. A system absorbs strange events the way oceans absorb storms. It moves, it adjusts, and then it returns to something that looks like calm even when the calm is only the surface. That's why the most unsettling part isn't that the spacecraft went silent, is what followed. How quickly silence becomes normal, how fast the absence of data turns into a blank space people stop looking at, How easily the most valuable unknown is filed under the most convenient label, because convenient labels keep the machine of daily life running smoothly. And daily life, in the modern world, depends on orbit so thoroughly that we don't even recognize orbit as a domain that can become stressed. We experience it as a service. Services are supposed to be invisible. When they aren't invisible, people get angry. So the system learns to hide strain. The system learns to normalize weak signals. The system learns to keep producing the same outputs even when it has to work harder to do it. That is the quiet trap of success. The Lost Close Observer is a symbol of that trap because it shows what happens when a rare opportunity collides with a system that doesn't prioritize environmental measurement as a default. One window arrives, one witness sees something up close, and then the witness is gone. Maybe it was coincidence. Maybe it was age. Maybe it was an ordinary failure that happened to land on an extraordinary date. But even if it was coincidence, the outcome is the same. We lose the one dataset that could have made the next pass less ambiguous. We lose the baseline we needed to ask more precise questions. We lose a chance to turn suspicion into measurement. And without measurement, the narrative returns to comfort, because comfort is what systems select for when they don't have to confront a cost directly. Now, Atlas is returning to the part of the solar system that contains our most fragile dependency. Not fragile because it's weak, but fragile because it's crowded. A crowded domain doesn't give you room to be sloppy. It doesn't give you room to be slow. It doesn't give you room to call weak signals routine indefinitely. Crowded domains punish delayed understanding, because delayed understanding forces reactive behavior, and reactive behavior tends to create the same outcome everywhere. More traffic, more complexity, less margin, more vulnerability to the next subtle stress. So the real ending here isn't a prediction, it's a choice point. During the closest window, the world will do what it always does. It will look for the most visible story. It will look for the best images, the sharpest renders, the most memorable talking points. It will ask the easy questions that sound profound. Where did it come from? How old is it? What is it made of? Could it carry life? Those are fair questions. They're valuable. But they are not the questions that determine whether this past teaches us something about resilience. The resilience questions are quieter. Did the environment around the object differ in ways our systems can detect? Did anomaly fingerprints cluster in time and geometry across independent fleets? Did we see changes in link margins that could not be explained by known space weather? Did attitude systems show a synchronized rise in corrections? Did thermal signatures drift in a corridor that aligns with the pass window? Did we actually set up the monitoring to be able to answer any of that? Or did we once again treat the window as a spectacle and then act surprised when the data we needed wasn't captured? Because the pattern that makes this story worth telling is not Atlas itself. It's our recurring habit of converting rare opportunities into soft conclusions. We tell ourselves that the absence of obvious disruption is proof of safety, even when we didn't measure the right things to justify that conclusion. We tell ourselves that a system that continues to function must be stable, even when stability may be purchased by hidden effort. We tell ourselves that the sky is empty enough to be forgiving, even as we fill it with machines that depend on thin tolerances. That habit is how you build an archive of regrets, and the phrase, "we missed this for 20 years, is not an accusation. It's a description of how complex systems fail culturally. No one wakes up and decides to miss a slow risk. You miss it by doing what feels rational every day. You miss it by prioritizing uptime over curiosity. You miss it by treating weak signals as background because you've been trained to look for strong ones. You miss it by allowing competitive incentives to keep anomaly fingerprints private. You miss it by assuming the baseline is static because it has been static enough. Then one day you unify the record and discover that static enough was never the same thing as static. If you want the story to land without deception, this is the honest statement that holds everything together. Atlas does not need to be a threat for this to matter. It only needs to be a rare test case. A rare event that passes through a crowded, fragile infrastructure layer and gives us a chance to see how our systems respond to unfamiliar conditions, even if those conditions are subtle. The failure of the close observer is not proof that Atlas causes harm, it is proof that we do not get unlimited chances to learn, and that losing one witness is enough to turn a measurable episode into a debate that lasts years. So what does an honest ending sound like if it refuses to turn into a headline? It sounds like a quiet warning about how we define normal. Normal is not nothing broke. Normal is we measured and the baseline held. Normal is not a few anomalies are routine. Normal is we checked whether the anomalies clustered, and they didn't. Normal is not space is harsh. Normal is we know which harshness is expected, and we can see when it changes. When you adopt that definition, the lost close observer stops being a sad footnote and becomes a signal flare. Not a flare that points outward at a mysterious object, but a flare that points inward at our own priorities. It tells us what happens when we don't build measurement into the default. It tells us what happens when we rely on luck to preserve opportunity. It tells us what happens when we allow comfort narratives to substitute for environmental understanding. And then it asks the simplest question a mature system can ask. What would we do differently if we could go back? The answer isn't cinematic. It's boring. It's building a shared watch list, agreeing on comparable anomaly tags, widening logging windows around the pass, coordinating among operators to look for correlation without exposing sensitive details, and treating any weak clustering as an environmental episode worth analysing collectively while it's still happening. It's preserving margin, not spending it to keep everything looking effortless. It's letting the quiet signals be the story, because quiet signals are where infrastructure either matures or repeats its mistakes. That's the real loop you either break or reinforce. You can reinforce it by doing what busy systems do, normalize, patch, replace, move on, or you can break it by doing what mature systems do. Measure early, correlate, share enough to see patterns, and treat invisibility as a reason to pay attention rather than as a reason to relax. Because invisibility is not safety, it's just invisibility. And if there's one last thing worth saying, it's this. The universe doesn't adapt to us. We adapt to it. We can't negotiate with particle physics. We can't demand that visitors arrive on convenient trajectories. We can't insist that rare windows extend until we feel ready. But we can decide what kind of orbital civilization we want to be. One that treats orbit like an infinite platform and learns only after expensive surprises, or one that treats orbit like shared infrastructure and learns while learning is still cheap. Atlas will pass either way. The spacecraft that saw it up close is already gone either way. The only difference is what we do with the chance that remains. Because if the next window closes and we tell ourselves nothing unusual, without being able to prove we actually looked, then we will have done the most human thing possible. We will have protected comfort at the expense of understanding. We will have protected the illusion of stability at the expense of resilience, and we will have guaranteed that the next interstellar visitor, or the next environmental episode, will feel more mysterious than it needed to feel, not because the universe hid the truth, but because we trained ourselves to ignore the language it uses, the language of weak signals, the language of patterns, the language of slow accumulation, and that language will keep speaking whether we listen or not. So this story doesn't end with a prediction, it ends with a responsibility, not dramatic, not loud, just unavoidable. If we want orbit to remain a foundation, we have to treat quiet events like Atlas as chances to practice attention while attention is still optional. Because once attention becomes mandatory, it's usually because the bill has arrived, and the bill in crowded systems is never paid all at once. It's paid through shrinking margin, through rising workload, through fragility that only reveals itself when the world needs stability the most. That is the price of our satellites, and it's a price we can either measure early or discover late.